Hello class, welcome to chapter 2, Continuity. Plainly speaking, if you had an unbroken curve, then you can say that it's continuous. That implies continuity. Now if I were to define this in math, then I would say the function f of x is continuous at c using the limit notation. Okay. So let me write that here. The function f of x is continuous at c is some point, if limit f of x as x approaches c, you know how that's usually equal to L, right? Capital L. We're saying that should be equal to the function value, f of c. So at c, the function must be defined. That means there will be no holes at that point, and you will actually see the function is continuous with the either the continuous stretch of the graph or it's indicated by a solid dot. So that is what this actually tells us. And here again, just like the limit situation, if your graph really is if it goes indefinitely on both ends, then you can have this continuity at every point. But if you have your graph kind of starting and ending, then you can have the graph with just one-sided limits. Therefore, there will be also one-sided continuity. Okay. So let me give you a graph to kind of help us understand this better. So in this graph, you can see that we have the graph running from A to B, and we are intentionally keeping it limited so it's not going indefinitely on both ends. So what we see is that in at A, right, if you check the continuity at A, you can see that you can approach this limit from the right, but you don't have something from the left. And so that's the end. And likewise at B, you can approach the limit from the left, but not from the right. But then if you look at the C value, if you look at C, then you can approach the same limiting value from the left and from the right. And what you notice is throughout you have these solid dots, meaning there are no open circles to indicate a gap in your function. So if we choose any point C, if we want to call the function continuous, then we should be able to approach that point from both the left and from the right, and that value must be equal to f of c. So this is, because it's part of the function, that c value should be plugged in to get the corresponding y value. Okay. Now if we look at A has one-sided continuity. So because we are approaching from the right, we will have right continuous. This is right continuous. At A. That means if you took the limit f of x as x approaches A from the right, so A plus, that will give us f of A. And here for B, that will be left continuous, so it's one-sided, at B, which can be written as limit f of x as x approaches B from the left, so a minus, will be f of B, because it's the function at that value B, right? So that is the general idea. And of course, two-sided continuity would indicate this definition we have up here. So I'm going to present to you a formal definition with the meaning of interior point and end point. So again, you can see what it literally means. End points in this case, in this example, would be A and B. And the interior point is any point that is between A and B, because the function between A and B, the blue graph, the function between A and B is continuous. So any value between A and B would be the interior of A and B. And so the definition would talk about the interior points, because we know that at the end points at A and B, it is not two-sided continuity, it's a one-sided continuity. So if we want to talk about two-sided continuity, it is assured within A and B, so the interior values of the interval A to B. So here's the definition, and let me read it. Interior point. If a function y equals f of x is continuous at an interior point C of its domain, if limit f of x, x approaches C, is f of C. I wrote that right up here, right? But see that they use the language more formally using the bringing in the interior point. Endpoint. A function y equals f of x is continuous at a left endpoint A or is continuous at a right endpoint B of its domain if limit f of x as x approaches A plus is f of A, or limit f of x as x approaches B minus equals f of B, respectively. So remember again that when you get the idea of the concept, you also have to expose yourself to the formal definition, and that's the reason why I bring that in and I read it to you, so that you'll get used to this format, this kind of language, because a formal definition kind of covers all the base and provides us the premise, the background for the theorem or the definition to work. And so sometimes, you'll have to just understand from the definition. And when you have a problem given to you and it requires critical thinking, the only way to understand is to fall back on the definition. So I'd like you to develop this sense of reading definitions. Don't skip them because you see that it's wordy. Learn to read them so that you understand the premise for which this will work. Now, along those lines, we have a definition for the continuity test. So we said if it's an unbroken curve, it is continuous. But, that is too simplistic. So we really need to know mathematically, how do you know that a function is continuous? So here is the definition, and the definition comes with these 3 pointers. Let's read through it. A function f of x is continuous at an interior point, x equals c, of its domain, if and only if it meets the following 3 conditions. That f of c exists, meaning c lies in the domain of f. Limit f of x as x approaches c exists, meaning the function has a limit at x approaches c. And thirdly, the first 2 conditions must be equal to each other. So limit of f of x as x approaches c must be equal to f of c. The limit must be equal to the function value. Previously, we said we are not worried about the open circle. That's okay. We're only trying to see how close it gets to that value and what value it points to for the limit. So we didn't really mind about the open circle. And that is true with limits for functions. But when we talk about continuity, we are kind of upgrading it to a situation where we want the function value to match with the limit. And that way we can assure or use limits to define continuity or continuous functions. And as you can see, we have these 3 conditions that must be met for a function to be continuous in its domain. So that's again an important language there. It says domain because you can't just look outside the domain and say, oh, it's not continuous, right? A good example would be the rational function 1 over x. Let me say y equals 1 over x. Right? If you see there is a discontinuity, right? There's a break at 0. So if we look at it like that, then we'll say, oh, it is not continuous because there is a break there. But if you look at the definition closely, it says it is continuous at an interior point of its domain. So if you look at this, the domain itself says we can go from negative infinity to 0, union 0 to infinity. This is the domain for this rational function. So in its domain, it is continuous because the domain eliminates 0 already. Because if you look at the fraction, when x takes the value 0, 1 over 0 makes it undefined. So the domain is what makes the function defined. So it automatically will eliminate things that make it undefined. And therefore, for this rational function over its domain, it is continuous. So don't just go by the visual and say, oh, you said unbroken curve. So this is broken. The curves I see 2 curves. So you can't argue that way because the definition made it very clear for us about the role of the domain. Okay. Now in the following examples, what I plan to do is give you some graphs where our focus will be on an interior point x equals 0, right? Because I'm trying to go by the definition here. And so I want to see a function f of x is continuous at an interior point. We're talking about continuity at a point. Later on, we'll be talking about continuity for the entire function. But if you think of it intuitively, if it is continuous at every point on the graph, that means it's continuous everywhere for the entire function, right? So we start off by looking at continuity at a point. Can we approach from both sides with a limit? And in particular, does that limit value actually match with the function value? Because if it approaches, if the limit exists from both sides, we simply say the limit exists. We did not talk about the continuity. But if it is matching with a function value, then we upgrade it and call it a continuous function. So let's take a look at this example. And as I mentioned, we'll be focusing on interior point x equals 0. Okay. So in this first graph, we have when x is equal to 0, there is a hole, right? When we consider 0. In the second graph, there is a hole, but there is a solid dot there. So let's think about this and consider the three conditions. So condition 1, let's see if that works. F of c exists. So c must lie in the domain of f. Is 0 in the domain of f? I'm sorry, not C here, 0. 0 lies in the domain of f in the second graph. In the first graph, 0 has a hole, right? So there is a break there, which means the domain would be negative infinity up to 0, union 0 to positive infinity with a break at 0. So the domain will eliminate the 0 for the first one. But for the second one, the 0 is part of the domain because I see a solid dot at 2 for the 0. So when we look at 0, we see that it's defined at 2. So the first one did not meet that condition. So right there, continuity fails for the first graph. Okay. Now, even if one condition fails, the test fails. You know that. So all three must be satisfied. So then I look at the second condition, which says the limit must exist. Okay. Now the first one failed, so it's really not required for us to continue with the test. But for the sake of illustration, I want to use that as well. So if you look at it from the left and from the right, do they both point to the same limiting value? Yes, the same value is 1. The same is true with this graph too, because this is, I would call this discontinuity. Situation, and this one will be called removable discontinuity. Now, if you recall stuff you learned in intermediate algebra, when there is a hole, what we did was we used piecewise function to fill that hole, cementing that gap by assigning another point for that hole so that the domain is continuous. So the second graph actually goes all the way from negative infinity to infinity. Even though there is a hole there, that hole is kind of filled at a different point on that same 0. So along the y-axis, we found some other point. We could have chosen 1.5. We could have chosen 0.7. Any number other than that hole where it occurs at 1. Anywhere other than 1 on the y-axis, we could have chosen a point and used that to fill that hole, to make the domain defined for all real numbers. That's why we call it the removable discontinuity. Okay. Now, or you can actually fill the hole right there and use the piecewise function to separately define a point at 1. And so it's like two pieces, but they both merge and gives you that one continuous graph. All right. So limit exists. Yes, we know that the second condition is true. What about the third condition? Does the limit equal the function? Now for the first one, yes, we saw that it's not defined at 0, so that's not going to work. But for the second graph, we have the limit of f of x as x approaches 0 to be 1. But, oops, not another point. We found that the f function, the function f of 0, actually pointed to the 2. So you see that there was no match. So there was a mismatch there. So this is a case of discontinuity where the test works in one or two conditions but fails in the third condition, right? So discontinuity, meaning just a hole or a hole with another solid dot to fill that, are called removable discontinuity. Okay. So here's the next example. Here we have, again, our focus is 0, right? The interior point is x equals 0. Write the x properly. Now, you clearly see that as we approach 0 from the left and from the right, there are two separate pieces, and they are showing limits at different values. So if I took the first condition, does 0 lie in the domain? And we say yes, 0 lies in the domain, because even though there is a hole here, it is compensated by the solid dot here. So it seems like all the values on the domain are defined. So if you look at the blue, leftmost end of the blue to the rightmost end of the blue, there were no gaps, meaning all the values were defined. Okay. Now if at 1 also we had an open circle, that means we have a discontinuity at 0 and it fails in point 1. So I would say f of 0 exists. Okay. So C lies in the domain of f. 2. Does limit f of 0, limit f of x as x approaches 0 exist? So limit f of x as x approaches 0. So that means you approach from the left and the right and they must give you the same limit. That doesn't happen. Actually, the left-hand limit as you approach 0 from the left, that gives you the value 0 on the y-axis. And your limit of f of x as x approaches 0 from the right gives you a 1. Together, you know that the limit does not exist. So it fails in the second condition completely. We don't have to go to the third condition. Nevertheless, we'll check the third condition. Even if the third condition holds true, it still has failed because the second condition did not hold true. All right, the third condition would be this limit f of x as x approaches 0 must be equal to f of 0. Now f of 0 would be the 1 because that is what we have. Now only the right side limit has a 1. Together the limit here does not exist, and this one is a 1, so they are not the same. So this one fails because it is a jump discontinuity. That's the name for it. It jumps right at 0, so we call it jump discontinuity. We'll take a look at the third example. Once again, we're talking about what happens at the interior point 0. So this clearly is a rational function, 1 over x squared, right? And let's again test the three conditions. Now, is 0 part of the domain? Right there, that fails. So f of 0 does not exist. I'll just say D and E. So it fails right there. But if you went for the second one, you see that limit f of x as x approaches 0 from the left. You see that the blue graph actually approaches infinity, right? And limit f of x as x approaches 0 from the right. That also, right, as we approach 0 from the right, the left also pointed to infinity. So together they gave us the same value. So limit f of x as x approaches 0 exists in the sense that they both give us the same value, even though infinity itself is not a value. They pointed in the same direction. And 3 would be, does the limit f of x as x approaches 0, is that equal to f of 0? Now this gave us infinity, but f of 0 is undefined, so we lost it there. So to avoid all this confusion and how do I interpret this, you just stop right when you have your first condition that goes off, Okay, so if your very first condition goes off, just stop right there. If it is your second condition where it doesn't work, stop right there. So wherever you first encounter a problem, you can stop right there. Okay, so this is called infinite discontinuity. Now this is a problem only because we chose 0, right? 0 is naturally not part of the domain. So we went after a value that was not a domain. So right there, that's the reason why this fails. But if you look at it in entirety, because 0 is not part of the domain, all other values will work, and so that will keep the function continuous. But for the sake of this interior point C equals 0, where 0 is not part of the domain, we have that infinite discontinuity. And the last example here, we've seen this before. We recall that y equals sine 1 over x kind of oscillates rapidly up and down, right? So basically it oscillates too much near 0. So you really cannot see what's happening at 0 because you really will not have that view. So right there you have this dismissed. You can't really tell if it's continuous or not, at least at 0. So we call this oscillating discontinuity. So we always want to use the 3 conditions for the continuity test to verify if we are looking at a particular interior point and see if it is continuous at that point. Now let's take a look at the properties of continuous function. We have the premise given to us, which says if the functions f and g are continuous at x equals c, then the following combinations are also continuous at x equals c. So f is continuous at c and g is continuous at c. Remember, these are 2 different functions. You have 2 different graphs running and they're continuous at c. So what they're saying is we can then add the 2 functions or subtract, do the constant multiple, multiply them, divide them, take the power and take the root. All these are supported by the limit laws, basically. So that is what we use to support this. Okay. So if your limits, if those 3 conditions are satisfied for f and g individually, then these conditions are also going to work. Now we also have additional rules that go with it for specific cases, like if you had a polynomial, is it continuous? If you have a rational, is it continuous? So we're going to do that as well. When we talk about the composite functions, composite of continuous functions, it says if f is continuous at c and g is continuous at f of c, then the composite g circle f is continuous at c. Let's focus on that for a moment. Okay. Now if you recall, f circle g was written as f of g of x, where you compose g inside f. So what we did was we usually plugged in the function g inside the function f, right? That's composition. And if it's g circle f, that's going to be g of f of x. G is the function inside which f of x is plugged in. So the order matters because what goes inside what, right? And so we're saying if f is continuous and g is continuous, then their composition will also be continuous. And all this is happening at c, at a particular point. So it's not for x, but it's for some c. Okay. So if I were to modify this, it's just like saying f of g of some point c is f of g of c, right? And it's for that point that it's going to be continuous in the composite form. And this is true provided f and g are each continuous at, meaning f is continuous at c and g is continuous at f of c, okay, because one is inside the other. So the order here matters. Okay. So f is continuous at c and g is continuous at f of c. So if you want to see this, in a linear fashion, let's say this is a point C, and this point will be f of C. This point is g of f of C. Okay. So what we are saying, if you go back to the definition, it says f is continuous at C. Okay. Let's think of this arch that helps us to make the connection. Oops, that's bad. It goes from here to here. That means f is continuous at C, right? Because it's f of C. And then we are saying, let's go back here, g is continuous at f of C. That means g is defined at f of C. So from here, you go to this. So you say g is continuous at f of C. That's how you can write g of f of C. Does that make sense? F is continuous at C means f of C, right? Because the function, if it's continuous, it matches with the function value. And what we're saying is, this theorem tells us, if this is true, then the composite G circle F is continuous at C, meaning you are bypassing this middle step and you're going all the way from C to here. And that will be saying G circle F, because G circle F is G of F of C, as I illustrated before. So that is what the theorem does. The theorem really helps you to bridge that connection from C all the way to G of F of C, which is a composition of two functions. And we're saying the composites of continuous functions are continuous. That's what this means. Now, what does the second one mean? It says limits of continuous function. So this is interesting. If G is continuous at the point B, and limit of f of x as x approaches C equals B, then the rule is this, okay? So technically what they're telling us is, if you took the limit of, okay, g of f of x as x approaches C, it looks as if all they're doing is they are switching the limit and they're switching the limit and the g. So when you do that switch, what happens is the g comes out and the limit goes inside. X approaches C, f of x. But we are told it's defined in the definition here that limit f of x as x approaches C is equal to b. So that means this whole thing here is b, which is the same as saying this is equal to g of b. So you have these two theorems, or these two definitions that teach you that composite functions are continuous, and there is a way we can deal with limits of continuous functions, okay, that are composite in nature. So going back here, we have these 7 conditions, and we have these two, and we also have other conditions. So let's write those down. Okay. So if I were to, let me just number this, okay, 7. So that will be like 8. This will be like 9, just to account for them. So condition number 10, or rather I should say properties. Property number 10 would be that polynomials are continuous functions. We know this from algebra, right? Polynomials, they vary by degree. So polynomial of degree 1 is a linear function, polynomial of degree 2 is a quadratic function, polynomial of degree 3 is a chair or cubic function. So we have all these functions, and they don't have any gaps, any breaks. They are continuous from end to end, so they are fine there. And 11 says rational functions are also continuous. And they are continuous in their domain. That's very important. This domain is where it's defined. Then we have absolute value functions. Are continuous. Then we have trigonometric functions are continuous. Again, it all has to work over its domain, right? In their domain. So quite obviously, they do have places where they become undefined. Not a problem with sine and cosine because they are continuous functions throughout. They have no restrictions because it's true for all real numbers. But tangent, cotangent, secant, and cosecant, these have asymptotes, remember? So these asymptotes indicate that the denominator became 0 at those points, meaning the function became undefined. So where the denominator takes the value 0, or in other words, if the function becomes undefined, you will see these asymptotes. Those are points where there will be discontinuities. So remember that if you're focusing on points that are not part of the domain, you will encounter trigonometric functions being discontinuous. So please bear that in mind when we consider the continuity. The continuity works only in their domain. Then we have identity functions. This is trivial because it is actually like a polynomial function of degree 1. So I just said identity functions are continuous. What are identity functions? These are nothing but f of x equals x, meaning the identity isn't lost. When x takes the value 1, f of x, meaning f of 1, is also 1. When x is -1, f of -1 is also -1. When x is 0, f of 0 is also 0. So you notice that if you were to draw the table to get your x and y values, you see that they are the same. The identity is not is preserved. So we call them the identity function. And then we saw previously too, the algebraic combination of continuous functions is also continuous. So these functions must be continuous to begin with. And that is what we saw in the top properties, right? So this is like a summation of what we saw in the beginning, meaning when we say algebraic combinations, we did the sum, the difference, the product, the quotient. So all those things are part of it. Okay. We'll take a look at an example now. So the question says, show that the following functions are continuous on their natural domains. And we start with the first one. Y equals square root of x squared minus 2x minus 5. So in order to answer this, we need to first figure out what the domain is. Okay, the domain is because of the square root. The square root function is continuous only from 0 to infinity, right? Because that's how it is. And because it's a root of a continuous, it's actually an identity function, the root of an identity function. So let me just write the description here. Square root function. This is square root of x. We're talking about square root of x. That has a domain 0 to infinity, right? Then what we see is this radicand, the expression under the radical sign, is a polynomial function. X squared minus 2x minus 5, and this is good for all domains. I mean all real numbers, sorry, all real numbers, negative infinity to infinity. And now what we need to understand here is that the square root function is square root of x, but x itself is an identity function, right? So I know we have a lot of conditions we saw. Identity function is f of x is equal to x. The function itself is x. So if you take the square root of, and f of x is continuous, right? Identity functions are continuous. F of x equals x is continuous. So if you take, let's go back here quickly. So if you talk about the roots, if f is continuous, then its root is also continuous, right? And it's defined on an open interval containing c. So the root of a continuous function is also continuous. That's great. And that's the idea we're trying to emphasize here. So if I combine these two, the square root, right, instead of x, I replace it with x squared minus 2x minus 5. Meaning, in the place of x, I'm plugging in x squared minus 2x minus 5, which is basically the idea of composition. Composition of x squared minus 2x minus 5 in square root of x. Right? And we just saw also that if two functions are continuous, then the composition of those functions is also continuous. So, and all this is going to happen in their natural domain, right? So that is what we have here. So we kind of reason out by looking at all the combination of these properties, and then we say this implies that y equals square root of x squared minus 2x minus 5 is continuous in its natural domain. All right, now let's take a look at another one, b. X power 2, let me write here, y equals x power 2 over 3 divided by 1 plus x power 4. Okay. All right, now we have to break this up. Y equals x power 2 over 3 over 1 plus x power 4. Focus on the numerator. The numerator is nothing but the cube root of x squared, right? X squared is a polynomial function, and the root of a polynomial function is continuous, so this is continuous. If you look at the denominator, 1 plus x power 4 is a polynomial, so that is continuous. So the numerator is continuous, the denominator is continuous. Nowhere does the denominator become 0 because no value of x will make it 0, right, because of the power 4. So this implies f, so let's say this was, just for convenience, let's call this f and let's call this g. That means f over g is also continuous by quotient property. And therefore we can collectively say that y equals x power 2 over 3 over 1 plus x power 4 is continuous in its domain. In this case, it's really interesting because the domain for the numerator is negative infinity to infinity, because the cube root can accept negative values in the radicand, so no problem. But if you look at it, x squared, so it's going to get squared, so you won't really get a negative radicand. So we got that. And the denominator is a polynomial. In particular, it takes all real numbers because it's not going to be affected by any value to make it 0 in the denominator. So because of the special condition, here the domain is everywhere, all real numbers. So totally fine. And so the quotient comes out to be continuous. Okay. Part C is y equals absolute value of x minus 2 over x squared minus 2. So for this, just focus on what is inside the absolute value bars. So if you look at what is inside, the numerator, I'll just call it NR, is a polynomial, right? That means it's continuous. The denominator, dr, is also a polynomial, so it's continuous. So the fraction, numerator over denominator, a polynomial over a polynomial is basically a rational function. So you can see it as a rational, and you know that is defined, that is continuous on its domain. So this is continuous everywhere, and together, if I were to see this, this is going to be continuous except when, so you'll have to see where the denominator becomes 0. For that you have to set your denominator to 0. So x squared equals 2, x equals plus or minus root 2. So if x takes the value either plus or minus root 2, we have a problem. So the domain has to eliminate these two values. So that's the natural domain for this. You know, if you actually go back to the quotient condition, I know it's a long way back. Look at this, it's f over g provided g is not equal to 0. The denominator should not be 0, that's part of the domain. So that is what we are doing here too. So this is where the domain, so I'll have to say not equal to, because you don't want it to be equal to 0 then. So we do not want in our domain, so this is a restriction in the domain, in the natural domain. It's a natural restriction because that is how the quotients are defined. Alright, so now that you've got this, now we have established that x minus 2 over x squared minus 2 is continuous in its natural domain, and we have absolute value inside which it is, so it's like having an x there. We know absolute value functions are also continuous. So if you compose this inside this, composition of these two continuous functions will produce absolute value of x minus 2 over x squared minus 2, which is composition of functions, and we know that is continuous. So these problems really help you to think, to see what are the valid ways in which I can use a combination of these properties to determine the continuity of these functions on their natural domain. Okay. This is called continuous extension to a point, and I want to recall that we've seen this graph before, y equals sine theta over theta. In fact, we use this and then we said the limit of sine theta over theta as theta approaches 0 is 1, right? But we see that there is that open circle there, and so the continuous extension to a point is that for this graph it is continuous everywhere else except for that value against 0, right? And therefore if we can fill that, and I discussed that under removable discontinuity, if we can fill that hole, okay, then we can make it continuous. We can't just fill that hole because that will change the function, you know, it will not be still sine theta over theta. Now for this we use piecewise function. Okay, so what we're doing is I'm showing this this area. How do I show this? It's like I'm zooming this area. Okay, I'm deboxing it to kind of show you that that's a zoomed version. Now the blue function is the original f of x. Okay, and the red function has the capital F of x, wherein my function has been adjusted to have that hole filled with a solid dot. Okay, so what we do is we use piecewise function to fill the gap. So I'll give you the general version for this. What we do is we create a new function, capital F of x, right, like the red one, it's a new function, wherein the original function sine theta over theta, let's call that f of x, right? That function is kept as it is, but you know that that function had 0 as not part of its domain, right? So we'll just keep it in its domain. So if x is the domain, is in the domain of f, so that will be the one with a hole. And then to fill the hole, you know where the hole is. The hole is at 0, 1, right? So if I could define another function which is basically 1, then I can fill that for that one. So in general, there could be some number, right? If the whole was happening at 2, then it'll be 2. If it was happening at 7.9, it'll be 7.9. So in general, I call it L, capital L, and that L will be if X is C, the place where you have the domain disconnecting, right? So for the sake of this problem, my capital F of X will be the small f of x, which is basically sine theta over theta. And this is, what's the domain for this? The domain for this is negative infinity to 0, union 0 to infinity, because there was a break at 0. And the 0, where the break is compensated at 1. So the other piece will be 1, comma, x equals 0, because 0 is where you had the disconnect, right? So that will be where x is equal to 0. Here x is any number that belongs to this interval with a gap. So this is what we do, so that when we fill it, okay, let me come back here. When we fill it and go back here, it is got two pieces, where one piece was the blue function, the other piece was the pink dot. But together, if you see them in the piecewise function setup, it is a continuous function that is defined at 0 as well. Okay. In fact, that 0 becomes the function value at 1, and therefore it helps you to see a complete fulfillment of your continuous test conditions. So all the conditions are fulfilled when you utilize this this piecewise function format to provide an extension, a continuous extension for the function at that point, right? In fact, this is also the situation where you'll arrive at when you have a rational function and you reduce by cancelling common factors. What happens is the rational function, which is supposed to appear in branches, will reduce to, say, a linear function or something with a hole. And so that can be overcome if you use the continuity or continuous extension of f. Let's take a look at some of the problems involving trig functions. So let's find the limit of cosine 2x plus sine 3 pi over 2 plus x as x approaches pi over 2. So now if you have a limit of cosine of a function, I want you to see it as limit cosine of a function. Right? So that's something in x, cosine of some angle. Okay. So it's usually cosine of some function, right? So the function would be an angle. In this case, the angle is this function. So we know that the limit of composite functions, right? The limit of composite functions, excuse me. So let me write here, it's easier to understand it as a function, like I wrote it in the beginning. Okay. So cosine of an angle in this case is a function, so it's nice to keep it that way. That property, limit of composite functions, tells us we can switch the limit and the cosine. So what this allows us to do then is bring the cosine out and send the limit in, because you can find cosine of a number, but how do you find cosine of this expression? So that's where this property comes in handy. So then I'll quickly say this was the limit of composite functions. This was one of our continuity properties, right? Okay, so now it's a whole lot simpler, because you just have to plug in for pi over 2. So 2 times, I just write parentheses for all the x's we have to substitute, and then I will plug in for the x value. And so here 2x, right? So it has to be pi over 2. I'm applying the limit, and then this is 3 pi over 2, and this is going to be pi over 2. It's so important to know how the parentheses work, because then we know how they are grouped. The 2's here cancel off, leaving us with pi plus sine. This is 3 pi over 2 plus pi over 2. They have the same denominator, so add them. That will be 4 pi over 2. I'm going to show that calculation here. That's going to be 4 pi over 2, which reduces to 2 pi. Okay. So then this becomes cosine pi plus sine 2 pi. Go to your unit circle from trigonometry, and if you find what sine 2 pi is, again, of course, keep it in radians. Cosine of pi plus sine 2 pi is 0. That's equal to 0 from the unit circle. And so we come back here and say, okay, that's pi plus 0, which is basically cosine pi. And cosine pi, we know, is -1. That comes from the unit circle as well. And so we use trigonometry in these kind of problems as well, right? How do you find, in the next problem, limit of 3x over sine 11x as x approaches 0? You see the sine 11x and x approaches 0, you must be reminded of that particular rule we saw about sine theta over theta. The limit of sine theta over theta as theta approaches 0 is 1. Try to use that here. Okay. So how do I use it? I have to have, this is 3x on the top, that's fine. But I have to have sine 11x, a matching 11x in the bottom, right? Isn't it? If I had a matching 11x in the bottom, then that would allow me to use this. But I can't just bring in 11x, so I multiply on the top with 11x as well. Remember, all this is happening in the denominator, but I'm still learning to balance it off. Okay, so my hope is that I will use this separately and this separately. Okay, so clearly these x's cancel off. That gives me 3 over 11 that can be pulled out, leaving me with limit x approaches 0, 1 over sine 11x over 11x, because they have to be matching, theta and theta. And now we are ready to apply the limit for the numerator and the denominator. So this is 3 over 11 times limit of 1 as x approaches 0 over limit of sine x, 11x over 11x as x approaches 0. And we know from the property above that I just showed you, this is going to be equal to 1. And the top, limit of 1 as x approaches 0, there's no place to plug in for x as 0, so it's a constant, so that is also equal to 1. So this actually is 3 over 11 times 1 over 1, which is basically 3 over 11. And that will be your answer. For this problem, we didn't really have to go into trigonometry, we just used one of the properties from calculus itself to answer this. Okay, let's go for the next one. Find limit of 1 minus cosine 6x over 4x as x approaches 0. Again, this setup we've seen before. It's a question of recalling. And so what we saw was limit h approaches 0, 1 minus cosine h over h is equal to 0. Okay. Now, sometimes it can have the other effect also. So h approaches 0. It could be cosine h minus 1 over h to be 0 also. Because after all, the order has changed, but you know that 0 takes neither positive or negative, so we are not going to see a change in the value in the answer here in this case. So it could appear in one of these forms. So we have that order here. Alright, for this again the h's must match, right? The h on the top, h at the bottom, and h in the limit. So so we have x as the common variable, so no problem there. Now I have the cosine 6x, I have to match it with a 6x in the bottom. And that again can be achieved if we did a little algebraic manipulation. So 1 minus cosine 6x. Remember I showed you this technique where I separate them on the top and the bottom like this, so that I could insert this 6x that I desire up and down, okay? And then this allows me to basically cancel off these x's. Even the 6 and the 4, 6 is 3 and this is 2. It simplifies, right? So then I can pull the simplified 3 over 2 outside, and I'll have limit x approaches 0, 1 minus cosine 6x over 6x. So it's matching. If it matches, that's fine. But if you wanted to see it in terms of h, you can also say let h be equal to 6x. Okay? So that means 3 over 2, limit of h approaches 0, because x is now changed to h, 1 minus cosine h over h. And that is strikingly exactly the same as the formula itself, but that we saw is equal to 0. So technically this is going to be 3 over 2 times 0, which is 0. So your answer on this one will be 0. So the next one said find negative 5x plus 1 minus cosine x all over x. Then what you see here is that we have that 1 minus cosine x over x situation partially, but there's negative 5x is in the way. But that's not a problem, because again algebra allows you to separate the fractions like this. So I have this 1 minus cosine x over x separated from this, and this in turn gives you x is cancelled off. So then all this is happening inside, right? So then we can separate them by applying the limit to each individual term. So that's limit of negative 5x approaches 0 plus limit 1 minus cosine x over x as x approaches 0. And because this doesn't have any x, this comes back as negative 5. Because of the rule, this becomes 0. So ultimately you get negative 5 out of this. Now in our next problem, it is find limit cosine 2x, let's say 2x over 3, and that's the angle part, plus tan x over 2, and that's when x approaches pi over 2. And of course this is all encased here. So here again we can apply the limit directly and see what happens. So this implies we have cosine 2x over 3 plus tan x over 2. And remember, I'm putting in parentheses for the place of x so that I plug in correctly. You know, if they gave you a negative pi over 2, then remember to make sure that the sign is managed correctly, and then you'll have to use the odd or the evenness of the function from trigonometry. And we learned that cosine and secant are the only even functions, which means they will absorb the minus, and the other four functions, sine, tan, cosecant, and cotangent, the other four functions, trig functions, will all be odd, which means if it has a negative angle, the negative will go in front of the function. So you have to recall all those concepts as well in here. Alright, let's solve this one. So the 2's cancel off here. That gives us cosine pi over 3 plus tan. That's pi over 2, which means it's pi over 4. And now you can use your unit circle and come up with the answer. So cosine pi over 3 will be a half, plus tan pi over 4, tan 45 degrees, is sine pi over 4 over cosine pi over 4. And you can see that in the unit circle, your sine pi over 4 is root 2 over 2. So I'll just write that here, root 2 over 2 over cosine, which is root 2 over 2. And so that's going to be half plus 1 and a half, which is 3 over 2. So that's how you apply. So because trig itself was a separate study, you did a semester of trigonometry, that you'll have to recall them. So go back to your notes, hold on to them, and if there are some steps that are missing in explanations or things like that, you want to really go back to that trig lesson to refresh yourself on what they used, what technique they used. Because at this point in calculus, we will not be able to go back and teach all over trigonometry. We will definitely help you to make that connection, and I will definitely help you to see, like I showed you, how tan pi over 4 is obtained as sine pi over 4 over cosine pi over 4. So we can do that, but we're not going to. You can't expect to learn trigonometry at this time. That will not be, that won't work. Okay, so I really recommend that you go back and look at those notes, and then we will continue on. Now, when we talk about limits involving infinity, we understand that all the limit laws we saw, right, those properties and the laws, they're all true when we replace the limit as x approaches c by limit x approaches infinity or x approaches negative infinity. Okay, so what we're saying is you can now expect to see x approaches infinity like this, giving you a value L, or it could be limit f of x as x approaches negative infinity, giving you a value L. Or we're saying we could also find functions x approaches c giving you infinity, or limit f of x as x approaches c giving you a negative infinity. So you can find infinity involved either as x approaches that or as a limit itself, as a value. So what we do is we are now trying to accept these also as results for finding limit. So let's take a look at some examples here. So we have to find the limit, or evaluate it, let's say, sometimes. First one is limit of (5 plus 1 over x) as x approaches infinity. Now, if this was our problem, now using the properties, right, the sum property, we can separate this as, I'll write it in the next step because that's our problem. This implies limit 5 x approaches infinity plus limit 1 over x as x approaches infinity. Okay. Now, because of the limit laws, we can actually substitute for x as infinity. Now, what we notice is that when you substitute for x as infinity, you notice that the first one doesn't have any x. So this comes back as 5. And here, when I plug in for x as infinity, it's 1 over infinity, right? It sounds silly, but infinity is a very, very large number. Positive infinity is a very, very large number. So a very large number sitting in the denominator makes that fraction really, 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 really small. Okay, that's the analytical way of thinking. So that makes it really, really small. But I'll also give you another way to look at it. If it's 1 over infinity, think of infinity is some number, right? Let's say a over 0. So because I don't want to keep some letter, I like to keep it as 1 over 0. It could be 7 over 0, 10 over 10,000 over 0. It doesn't matter what that number is. For simplicity, I'm going to understand that my infinity is like 1 over 0. Please understand that they are not equal, but I want you to see it that way so that you can reason out like this. So in the place of infinity, if I were to do the 1 over 0, by, when you divide two fractions, you take the first fraction, the numerator, times the flip of the denominator, right? So it's basically 0 over 1, which is 0. So you can see it analytically that as x as infinity that is a very, very large number, the fraction becomes very, very small. It's a very large number and the fraction becomes very small meaning 0. If you were to see it like what I just showed you, you can see that it actually comes down to a 0. So both ways help us to reason out as 5 plus 0, which is 5. So that's the answer here. Let's try problem B. X approaches negative infinity. So we have this expression pi root 3 over x squared. Okay. Now remember, again, you can use the properties, a combination of those properties, the limit laws. So if we approach in that direction, we see that the pi and the root 3 are constants. So we can pull out the pi and the root 3 out, leaving us with limit 1 over x squared as x approaches negative infinity. Yeah. So this again, you can separate it out as limit x approaches negative infinity. I'm going to separate the 1 over x squared as 1 over x times. So I am separating it and applying limit individually. 1 over x. So you have those three terms, the constant and this and this. We just saw, right? We just saw here that limit 1 over x as x approaches infinity is 0. Now what about negative infinity? Negative infinity would have had the negative, right? Maybe negative 1 over 0 is negative infinity. But it doesn't matter because 0 does not take positive or negative. So what we see here is that this actually comes down to 0 times 0. So all of this multiply out and that gives us 0. That's the answer for part B. Now if we look at part C, we're asked to find the limit of 5x squared plus 8x minus 3 all over 3x squared plus 2 as x approaches infinity. If you applied infinity everywhere, right, you can clearly see that x is not in the denominator, it's actually in the numerator. If you plugged it in, you're going to get infinity for the numerator and infinity for the denominator. It leads us to infinity over infinity. That is not desirable, right? So what we do is, our interest is to divide the numerator, okay, by the highest power you see in the denominator. Divide every term in the numerator and the denominator by the highest power in the denominator. So I'm going to write this, give some gap. So the highest power in the denominator is this x squared, right? So that's what we're going to do. We're just going to do divide by x squared. And I'll show you shortly the big benefit that we get out of it. Okay. What this does immediately is, if you have matching x's, it helps cancel off, right? Because you are dividing up and down, the balance is preserved, so we did not affect the value of it. So that is mathematically perfect. So if you were to cancel off, this goes away, 1x from there, and here again this goes away. So we are left with 5 plus 8 over x minus 3 over x squared divided by 3 plus 2 over x squared. Now when your x approaches infinity in your limit, this is the most desirable form for us. Why? Because if we can move the x from the top to the bottom, like in this case, we have all our x's happening in the fraction in the denominator. When we do that, we can again apply this situation. Limit of any number, doesn't matter. Anything over x where x is going to be infinity, right? When x is really, really, really large, then the fraction becomes very, very, very small, which is the same as 0. So it doesn't matter if I had a 1 on the top or 7 on the top or 10,000 on the top. All of these will give us nothing but something over 0, and that is what we desire. So when we apply it here, so 5 plus 8 over, it's very uncomfortable for me to write the infinity there, but I had to show you that I'm basically substituting for x as infinity, right? There's no meaning to say infinity squared because infinity is so large. Okay, so it's already there. It's so huge. You're not, by squaring it, you're not adding anything more to it. Okay. Alright, so we know that when I apply, I'm plugging in for x as infinity. You know that this becomes 0, this becomes 0, and this becomes 0. Okay. In future, I will not be plugging it in, but I will simply write that expression will approach 0. This is just for us to see through it in the terms of substitution. So all we're left with is 5 on the top, so 5 plus 0, right, basically. So 5 on the top and 3 in the bottom. So the limit for this was 5 over 3, right? That came out really, really nice. What number was this? C. So let's go to D. Limit 11x plus 2 over 2x cubed minus 1. And here x approaches negative infinity. So let's apply the same technique where the numerator is divided by, each term in the numerator should be divided by the highest power in the denominator. That over x cubed over x cubed. I'm so sorry, this was supposed to be x cubed. I have it as x cubed. X cubed minus 1, right? Yes, 2x cubed minus 1. And so that's going to be x squared cubed. Something's wrong. It's all x cubed everywhere, folks. Okay, I'm dividing it by x cubed. And then when I cancel off, that will be an x squared. This goes away completely. So limit x approaches negative infinity is 11 over x squared plus 2 over x cubed over 2 minus 1 over x cubed. When you apply negative infinity, we just saw previously that it doesn't matter if it is positive infinity or negative infinity, because this whole thing will become 0, and 0 doesn't take a positive or negative value, so it really doesn't matter here. Okay. That is a 0, and that will be a 0. So what we get after applying the limit is 0 over 2 minus, okay, I'll just show it to you individually, 2 minus 0, which is basically 0. So 0 is a perfectly fine number. We just got this to be 0. Now, if you think about the 1 over x situation, right? 1 over x is this rational function, right? And if you were to reason it out through the graph, we'd reasoned it out algebraically, right? We said as the denominator gets really, really large, the numerator gets the fraction gets really, really small. But I'm asking you, if we were to find limit of 1 over x as x approaches infinity, how would you answer that? For that, you go, oops, that's a bad color, so you can tell them apart, use blue. So as x approaches positive infinity, right? As we go, as x gets larger and larger and larger, notice how your pink graph gets closer and closer to the x-axis, which is 0 for the y value. And that's what we got. That is what it means to say that limit of 1 over x as x approaches infinity is 0. Likewise, if you go in the negative infinity direction, as your x gets larger and larger and larger on the left side, in other words, very, very small, I should say. So as x becomes smaller and smaller and smaller on the left, you're going very, very close to negative infinity. Look at your pink graph. Pink graph actually begins to trail close to the x-axis once again, pointing to 0. So the limit of 1 over x as x approaches negative infinity is also 0. Does that make sense? On the other hand, if you change root and you say, well, what if I approach 0? What if we approach 0? As you get closer and closer to 0, you see that your pink graph gets closer and closer to positive infinity. Now that's interesting, because limit 1 over x as x approaches 0 from the right, because it's 0 is not part of the domain, so it is discontinuous, so you'll have to look at the left and the right limits. So what limit of 1 over x as x approaches 0 from the right actually points to a positive infinity. And likewise, if you approach 0 from the left, So limit 1 over x, x approaches 0 from the left. You see that the pink part of the branch points downwards. So that's going to go towards negative infinity. Okay, so we have a play of values here. It's all between 0 and infinity, but if you look at the graph, it makes it a lot more easier. That is why I recommend that when you do something algebraically, you know you're getting the exact value, always cross-check it on the graph, and vice versa. If you got something on the graph, check it algebraically too, because now you have the ability, the strength and the tools to go between these two forms, between algebra and graph. So I strongly recommend that you use your graphing calculator to analyze what happens at a particular point or as x approaches a particular value. Okay? So here we see that. Now we've seen in algebra that this, when x approaches infinity you get a number, and when x approaches a number you get infinity. That play is basically your asymptotes. Okay, so these are basically your asymptotes, because for 1 over x you actually have two asymptotes. You have the vertical asymptote and the horizontal asymptote. So let me quickly define horizontal asymptote here. Horizontal. That says, with all the definition in the background, okay? So if you had a line y equals b, it's a horizontal line, so it has to be y equals b. So limit f of x as x approaches infinity will be some value b, which is the horizontal line, okay? Or it could be limit f of x as x approaches negative infinity, which could be that b. And that's what we saw in the case of 1 over x, that b was a 0 basically. So when we went towards positive infinity or towards negative infinity, we got a 0. And when we talk about the vertical asymptote, as vertical asymptote is present when your denominator becomes 0. So the definition for vertical asymptote would be the other way around. The equation of a vertical line is x equals a. So then we can say limit of f of x as x approaches a from the right, say. It could be plus or minus infinity. Or limit of f of x as x approaches a from the left, like we saw, 0 from the right, 0 from the left. That could approach plus or minus infinity. And that was your vertical asymptote. Okay. So if we look at some examples on this, we can see that we can apply this information to reduce our limits. So let's say we're asked to find the limit of x minus square root of x squared plus 16 as x approaches infinity. Okay. You must be curious to at least go back and check this on your calculator. But at this point we are going to use algebra to overcome this. What we see is if I directly apply infinity, right, the whole thing becomes infinity. And what we've seen is that when x approaches infinity, you didn't get it back in infinity, you got back a number. Likewise, when x approaches a number, you got back an infinity. So you don't get infinity in both places in the same limit expression. So that is one thing for you to look out for. And so we have here let me write this out. Limit x minus square root of x squared plus 16 as x approaches infinity. Now what we can see is the difference, infinity minus infinity is not clear. So we have to use algebra. What algebra technique can I use? Remember, we did this kind of a problem before, and when we had a radical, the way we went about it is to multiply up and down by its conjugate. Okay, so I am going to insert that conjugate here so that you can see that the conjugate of x minus root x squared plus 16 is x plus square root of x squared plus 16. And what you do on top, do the same in the bottom to keep the balance. because you cannot just insert any new term. Right? Now go ahead and multiply them out. That's going to be a plus b times a minus b format, the difference of squares. So it is so much easier if you simply did this. Instead of foiling it, you can just write it like this. Okay. Now we have limit x approaches infinity. That's going to be x squared minus x squared plus minus 16, I should say, because it's going to be like this, right? Because the root and the square will undo each other, you know that. They will go away. Thus giving us just the x squared plus 16. But that is happening in the parentheses, so this minus must be distributed. So this is your denominator. To save a step, I'm going to drop the parentheses here, but change the sign here to a minus. Okay? You can always rewind and see what I did there. So I distributed the minus to the parentheses, and therefore I'm dropping them after I have distributed. So the x squareds will get cancelled off, and we are left with negative 16. So limit x approaches infinity, negative 16 over x plus square root of x squared plus 16. So what we want to do here is we want to divide the numerator and the denominator by the highest degree, which is x. Okay? So limit x approaches infinity, negative 16 over. Now this requires strong algebra skills in the sense that you are able to see how to manipulate the problem. Okay. Now the purpose of doing this is, of course, the x's cancel off, and then you get this x on the top, so that when you apply x for infinity for x, that expression becomes 0. But here you have a square root and an x. So think again about how you can algebraically manipulate that. Now we know that this is negative 16 over x over 1 plus. Why not write this x as square root of x squared? That's possible, right? That way I can merge it with the square root situation that I have there. So what I'm going to do is draw a big square root and put x squared plus 16 over x squared. You see that? And if we do that, the biggest advantage we have is we can separate the terms. So that's negative 16 over x over 1 plus x squared over x squared plus 16 over x squared. Because remember, the ultimate goal is to get all your x's in the denominator whenever you have a limit of x approaching infinity. You don't want to do this if x is approaching 0, isn't it? Because you'll get the 0 in the denominator. At that time, you want all your x's on the top. But here, the approach is to get your x's in the bottom so that the infinity will make the fraction 0. Alright, so negative 16 over x, 1 plus square root of 1 plus 16 over x squared. Alright, now I'm going to apply the limit. When I apply the limit, this becomes 0, this becomes 0. So apply the limit, which can be seen in the next step. So that's going to be 0 over 1 plus square root of 1 plus 0, which is basically 0 over 1 plus 1, right? Square root of 1 is 1. So 0 over 2, which is 0. You can go down until you feel confident that the answer is 0. Don't be in a hurry and then say 2 or declare it to be something else, like a half or something. You know, the numerator was a 0. So we want to make sure that the denominator is some other number, not another 0. And we get that, and then we declare that the answer is 0. Now in your homework, you might see some other examples involving trigonometric functions. So please understand that you will need a strong understanding of your trig identities. So use your unit circle as well. Most of them are plugging in values, right? So you should know when you apply the values what coordinate it will be on the unit circle. So watch out for that as well. And so that winds up our this particular lecture on continuity. All right, class. So with that, we come to the end of our section on continuity, and I will see you in the next video. It's the end of chapter 2. So with this, we are done with chapter 2, and we had a series of topics that we covered in chapter 2. In my next video, I will see you in chapter 3. So thank you so much, and see you soon.